All right. So our first one is on KitchenAid gas range here. Um, the issue is that you've got when you turn on a bake cycle, it will ignite, properly ignites, you get a good flame. It runs for 20, maybe 30 seconds, and then it just shuts off and nothing. Basically acts as if it came up to temperature and was satisfied and shuts down. Um, the interesting thing is that that behavior is not present in diagnostic mode. If you run the bake cycle in test, then it will run just fine. How would we want to start going about troubleshooting this?
Start with my temperature sensor, probably.
Temperature sensor is a good thing, and the guy in this topic did check the temperature sensor, and it was in spec. Um,
And
so I think
Sam and Tim, what would that's good. I totally agree. Check the sensor. Just for the benefit of others who may not be following that, what would be the reasoning for checking the sensor?
Well, we know, if you're asking me, yeah, we know that it's turning on and it's baking or doing what it's supposed to be doing. But if it's prematurely shutting off, you could possibly say, hey, maybe it thinks that it's up to temperature, preheated already and shutting off.
Exactly.
My thing.
absolutely.
Exactly.
Now, if it's not the temperature sensor, then we kind of need to get into figuring out how exactly does this DSI board here work. So if we look at our inputs here, you can see we got these relay switches on the board that are actually how it gets its line supply for either bake or broil. It's got a neutral connection over here. It's got some connections to the gas solenoid valve. From looking at this, can you tell if there's anything that should be here that's not shown on this schematic?
Sam, zoom in a little bit on the DSI. Yeah, there you
Yeah,
Yeah, where's the igniter?
go. There you go.
exactly. Where's it's a direct spark ignition. That's what DSI stands for. Where's the spark? Um, so I don't know why exactly they decided to leave that off of this schematic. Maybe they were worried about guys going in there and trying to measure that spark voltage, and so they're like, let's just not even show it on the schematic. But
Anybody know what that spark voltage typically is in the range of? What kind of voltage is at that spark electrode?
You tell us every few months and we always forget.
It's like between 12 and 15,000 volts. It's got to be that high in order for that spark to jump the gap from the electrode to the burner base. It's a little 3 millimeter gap.
there it
So
is.
yeah, so you need a high amount of voltage to get the electrons to jump that air gap. And when the electrons jump the gap from the electrode to the bake burner tube in this case, those electrons are oxidizing air molecules. That's why you see a spark. It's that movement of electrons that, again, that we're dealing with.
Now, um, yeah. So of course, the DSI board does have those connectors on it, and if you look at a picture of it, like right here, you can see them. They even call it out. Output spark to the oven igniters. So you've got one connector over here. That's that J1 connector. And then over here, you've got your not just two, but three AC connectors here, these kind of high voltage spades here. So two are obviously, one for bake, one for broil. What's the third one?
Ground.
Exactly. That's the ground connection, this green one. Why is that ground so important? Anyone know?
The return, to sense the return.
Exactly. Yeah.
Yeah.
Return for the flame sensing, which this does have. This does have flame sensing. We'll get into why that ground is so important to the flame sensing in a second. Um, but yeah, so this connector here is where you have all of your low voltage stuff going on. So that is all of these pins. I say low voltage relatively, lower than the spark voltage. Your normal 120, or for the solenoid valve, it's actually a low DC voltage. They've got the spec for that. on which page?
So
Right here.
Sam, I had a question on
Yeah.
the ground. I
Mhm.
thought you needed the ground for the spark to go from the 12,000 to ground.
Well, it's
So-
jumping to the burner base, which is already grounded. But the
Exactly.
the function of that ground wire is so that the DSI board can sense that return current, which changes as to whether you have flame or not because of a thing called flame rectification. The current through that flame changes. So if you got a flame, it's going to be a different current than without a flame. The board knows this. It knows to look for that in the return current. So it's kind of listening for that. That's how it knows whether there's a flame or not, because the return current is different. So it's the
Yep.
ground wire is actually part of the spark circuit.
Yep. This is one
When-
of the few situations where you have a ground wire, an AC ground wire, that is a intended part of a circuit when it's normally functioning.
Right.
Where does
Most of
that
your
ground
AC,
wire connect to?
The chassis.
just the chat. That's how the
Okay, so-
DSI
okay.
board is monitoring the current in the chassis. So most of your AC loads, it's like L1 and neutral or L1, L2, that kind of thing. This is L1 and ground explicitly. And by the way, that 15,000 volt spark voltage, if you try to measure that, most of us use Cat 3 meters, which are rated at 600 volts. If you try to use a Cat 3 meter to measure 15,000 volts, you'll destroy the meter and maybe even hurt yourself.
Yep. So yeah,
So
if,
we should
if
try
you
that.
were absolutely, yeah. Yeah.
Don't try it at home, only in a customer's house.
You try it.
So yeah, if you want to follow the circuit here, just following these wires, let's say white is the bake spark. You'd go along through that white wire. It would eventually reach. Oh, looks like I was wrong. Looks like it was the brown wire. Doesn't make a difference. Goes through the brown wire, through this electrode, jumps this air gap. So for a moment, that air becomes part of the circuit because the voltage is high enough that it can overcome the air resistance. Goes into this burner, which is grounded. It is screwed into the chassis. Goes through the chassis, and then just up to this ground wire, which is also screwed into the chassis. So it goes through the chassis, through this ground wire, back to the board.
So you
Complete
got
circuit.
two ground connect points that are critical in this circuit. One at the bake or broil burner, either both, and then the
Yep.
other finally at the DSI board. And if either one of those are corroded, and this I've seen this quite a bit, you'll see corroded ground terminals for whatever reason. Rust is an insulator, and it will interfere with that. And we're talking microamps, by the way, of return current. We're not talking amps. We're talking microamps.
Mhm.
And that's all it's picking up. And it doesn't take much to interfere with that little bit of current flow. So
Yep.
the spark is high voltage and very low current. Kind of like static electricity, high voltage, low current.
So back to the this main connector here, this J1 connector to the board. That's where you've got all of your 120 VAC power inputs, both line and neutral, and those connections from the main board that go through these switches here, basically signaling the DSI which side of the solenoid valve. This is a dual solenoid valve, so you got one coil for bake, one for broil, and the board closes one of these switch to tell the DSI board which one to both open the valve for and to send spark to that igniter. So that's all on this same one here. And they've got these low voltage 8 to 18 DC, and that is the voltage that's actually for the solenoid valve here. It's just a DC solenoid valve. So they've got a little markup here showing how that works. Basically, as long as the DSI is receiving L1 through one of these switches, it will try to run the appropriate burner. And then as for that flame monitoring, flame sense, They've got actually a little table for this, which is nice. You don't often see this.
Oh, this is very
kind of
nice
info.
because it's sort of at a glance giving you the algorithm for the sparking.
Cool.
Yep. So this is if you look up here at the time, this is over a 4-second interval. Goes all the way from 0 to 3.54 here at the end. And so it's going to try to spark 4 times through that. Or well, not try to, it will continually spark through that, and it'll keep sending voltage through there because that's how it continues to monitor the flame. So it opens the valve, leaves that open for about half a second, then it will charge the capacitor on the board. These orange bits here are the capacitors. Charge up those capacitors, discharge in a spark, and then it looks for that return current. And I'll do that 4 times throughout. So basically 1 time a second. There's a whole breakdown here. I'm going to summarize this for you, but basically this is just saying that that cycle that we just looked at, it'll try this, and if after those 4 seconds it has not sensed that a flame has been established, it will cut off for 40 seconds. It wants to wait for any gas that was released to dissipate. Then it'll try again. If nothing, off for another 40 seconds. It tries 1/3 and final time. And if it fails to establish a flame then it goes into a lockout mode, which there's no indication of that on the control. It just goes into lockout until you press off or cancel on the keypad.
And by the way, these DSI boards, Whirlpool doesn't make them. They buy them from another manufacturer. And so it's standard. J1 connector, this algorithm of operation. This is typical of all DSI boards. And DSI is really not that mysterious. A lot of guys get intimidated by it, but if you've worked on car ignition systems, it's kind of the same thing with just a few extra features, flame sensing, for example, and this algorithm of running for 4 tries and then cutting out. But you got an ignition coil. The green things on the picture were the coils, and the red things are the charging caps. Sam, if you have that
Yes.
picture.
Yep, right here.
Yeah.
Capacitors here, charging coils here.
Yeah, so it's like a little mini car ignition system with some bells and whistles.
Again,
Um,
that ground return, it's through the burner. So the burner's part of the ground, the current.
Absolutely, and that's a great
Correct.
point, Tim. So this is especially good applicable to cooktop, gas cooktop with flame sense reignition capability. A common problem is gookus built up under the burner base that's interfering with that because it's the burner base sitting on that cooktop top that provides that connection. If you get gookus under there, that breaks it just like a rusted ground wire.
So where the burner bracket attaches to the frame, that's
Yep.
Yep.
Yeah, well, it actually, and so a common problem would, if that screw rusts up or gets wallowed out and loose, then that is a loose connection in your circuit. And that could interrupt the current going back to the DSI board, and it could be unable to sense that there's a flame.
On the
So that's
DSI,
Yeah, go
on
on.
the DSI board, you had 2 green charging coils and 2 orange capacitors. Are those one for bake and one for broil?
Yep.
Yep.
Exactly.
Yep, you've got
So
your
one of those-
spades for
Yeah, one of those
Uh,
coils will be putting out high voltage when bake is selected, and the other one will be put out for broil.
Yep. And then you got ground right down here. You can see the spades here. So that is all for our DSI. So we understand how that system works now. And what the tech actually ran into here was, we had to understand all of that to even troubleshoot this and make sure we understand what was going on. Turns out the problem was not related to like that whole system was working properly. It was working as we described. There was no interruption in the return path for ground. The board was able to sense current. What the tech did was he just did a voltage measurement put a meter checking for output to bake right there, and check that with reference to a neutral. And he found that at that 20 to 30 second mark into the cycle, so yeah, he was just losing the 120 volts here at P23 here. And so because he had eliminated everything else, the DSI board was working properly, the temperature sensor was in spec. The only thing for it was to replace the main control board. That's sometimes what you get, is that you get to the main control board after you've eliminated all the other possibilities.
This is called backing into the solution. So, process of elimination. So you've eliminated everything else. You're kind of only left with the one thing.
Yep. And as it turns out, that was in fact the problem. It started working properly after the main control board was replaced. So there was some failure perhaps within the logic of the board, because if you remember, while it would do this, it would act this way during a normal cycle, in diagnostic mode, it was perfectly capable of running the DSI board for as long as you wanted it to.
So in a bake cycle, there should always be 120 from P23 right there to
Yep.
J4.
Yeah, because that's the DSI board signal that it's supposed to be running the valve. Once it loses that signal, it will stop running the
It will
valve.
close that solenoid.
Exactly.
Yeah, the solenoid, and put in the put out the high voltage in the not shown electrode wire. And I think they don't show the electrode wire here because they don't want techs going in with their meter and trying to measure that voltage.
Yeah, it seems like I've seen this problem before, where it just doesn't want to continue. You could tell maybe it's an issue with the ground when it's trying to light, but if it's not trying to light, then you have to measure that voltage from P23 to J14.
Exactly. Well, and the reason we know the DSI board and the flame recognition is all working is because we have this information on the cycle. We know that it's actually a pretty short cycle. It only tries for 4 seconds, and if it doesn't establish a flame, then it will stop, try again, stop, try again. We had it running for 20 to 30 seconds. So it was able to establish a flame, and the DSI board was able to tell that the flame has been established.
Yeah.
So we know that the DSI board is working properly. Again, that with that and the temperature sensor both being good, that only leaves the main control board, really.
Which almost kind of makes me wonder if the actual temperature sensing component of the board was not the failure part. Do you see what I'm saying? Because
Yeah,
it would
good
actually,
thought.
Yeah.
Good thought. I mean, and that does happen. That's not an uncommon thing at all.
Yeah. I
Very-
mean, ultimately, we can only conjecture about what actually went wrong in the guts of the board, but yeah.
yeah, it's firing up for 20, 30 seconds or whatever, and it's saying, hey, we're hot enough, we can turn off.
Yep, that's a totally reasonable assumption.
Yeah, and that's happened a lot too. So yeah, very good, Tim.
All right, that's what I got for that one. If we're any more questions on that, any questions, anything else, any other thoughts that arose during that?
I had a question.
Sure.
Pardon my ignorance, but would there be any other testing points besides P23 to J14 that you could do that would garner the same results?
Oh, absolutely. Any other? In fact, I think that's kind of a silly neutral that I chose. That was just the first one that I saw. But probably if you were actually doing this, you would do from there to this one right on the board. So just the other to P63 right there, because that
I
is
like
also a hardwired neutral.
I like that a lot better. Yeah,
Yeah.
testing all from the board.
Yep. That's if you were actually doing this, that's the connector you'd be at, so you'd choose the most convenient points.
Yeah.
On the schematic, it's easy to draw a line going anywhere. When you're actually on the job, what you're working with is the physical reality of the connectors and the wires. And so this reflects that much better.
Now that we know what we know, why wouldn't the initial procedure be to make sure that the oven control is sending the signal to the DSI board?
So I mean, all the stuff that I went through about the DSI board, that was to make sure we understand how the DSI board works, because you need to understand how it works to know what your tests mean, to know what the behavior of the machine means. But yes, I mean the way you test this is very simple when you understand how it works. It is just doing this measurement. This would be the first thing you do is say, well, if it's cutting out after 20 or 30 seconds, I should see if the voltage from the main board is cutting out.
You guys familiar with black box troubleshooting? So this is how they taught us in the Navy. So we got a black box and it's got all kinds of weird stuff in it, but we don't care. It's not putting out something. So what's the logical troubleshooting response? If you got a black box, say the DSI board, just treat it like a black box, just a box with some numbers and letters on it. And we don't really care what's going on in there for the purpose of what I'm trying to illustrate here. So, and it's not putting out anything. You're not getting spark. It's not trying to open the valve. Just in black box troubleshooting, you go, okay, my black box isn't putting out outputs, but I know I need inputs for that black box to put out outputs. So my next quest is, am I getting the correct inputs for that black box DSI board to do its thing? So you can just treat it as a logical troubleshooting. You can do this with lots of things. There was another topic in appliantology where a guy wasn't getting output from a board or whatever, and he hadn't even checked for proper input voltages. And turns out there was a TCO in the power supply. It was shown right on the schematic that he posted, and that turned out to be open. So it's just inputs and outputs. That's basically black box troubleshooting.
Yeah. Now the DSI board, because they give us enough information on it, we don't have to treat it just like a black box. We have some idea of how it thinks, and how it behaves based off of that, based off of this chart and some of the other information they give us. But the main control, we do have to treat more like a black box. We don't know exactly what algorithm it has. They don't tell us.
So, and then right here, if you look up top there, it'll say, it'll show you the ohms of the solenoid coils themselves. And then also in the tech literature, it'll tell you that if either one of them is bad, neither of them will work. So
Correct.
for instance,
it does say that.
Yeah. So even if you had a broil, because we went on this, but I've been on this before, to where my tech, was struggling on the call, and it ended up being the broil solenoid was cracked on the gas valve, and so as it would heat, it would work fine sometimes, but as it would heat up, it would swell and then shut the unit off. Shut the flame off, and ended up being a cracked coil on that solenoid of the broil.
Interesting.
Yeah, and so it's reasonable then. Another reasonable thing to do if you're not getting any activity, no bake, no broil, is just check continuity through those solenoid valves, knowing that the DSI board checks continuity anyway before it starts applying voltage.
Yep.
A great point. Yeah.
Quick question. Could you go over again the where do you not test? You talked about high voltage. Just want to clarify, what do you not want to test?
Yeah, so that's they don't show it here on the schematic, but it's these wires coming off of here. Those are the spark output to the igniters.
Yeah, that's your high voltage. You don't want to
Yep.
put your meter probes in there.
12 to 15,000 volts. So
Yeah, and
far outside the range of your meter.
You could take a probe, put it in one of the either the white or brown wire, put your other probe in the green wire, fire up the spark, and your meter will blow up.
Wow.
So don't do that.
Yeah, I'm surprised that's not happened more often. I mean, that's
Yeah, because and that's the key piece of information there is knowing that you're dealing with really high voltage, low current, but high voltage. And it's the voltage that can still cause damage because the voltage exceeds the dielectric rating of the wire insulation inside your meter. That's what the CAT ratings are all about, is how much voltage can it stand without breaking down the insulation around the wire inside your meter.
Why is it low current? Like what? So, when you get shocked by your fingers near an igniter, like on a cooktop, or put your finger near the igniter in this scenario, with 15,000 volts, what's the cause of it being low current, but such high voltage? Why don't you, when you feel that and you kind of get shocked a little, why is it hurt less than 120? Is the low current due to the air? Like the air gap?
It's a couple things. You got the capacitor and coil working together. They have to charge up to produce that spark. So, and then once it does that instantaneously, once you get that spark, it's instantaneously discharged. So there's nothing to sustain the current. You'll just get that little impulse of voltage, and that's it. And there, you got it. Whereas if you grab a 120 and then grab a ground or a neutral with the other hand, you're getting sustained current. Electrons are being pushed through your body and oxidizing your body's tissue as it goes through.
So it'd be like
That's where you get the damage.
it'd be like turning on a fire hose for a split second and quickly getting hit with a burst of water and then it shuts off. It really wouldn't do, rather than leaving the fire hose on.
Yeah, it's that exactly. It's that travel of electrons through your body over time, and we're talking like seconds.
Okay.
Whereas the impulse that you get from a spark is a fraction of a second.
But if you had a source to leave 15,000 volts, that would kill you instantly or blow you into nothing.
Yeah,
Okay.
and it would have to you'd have to sustain the current too for it to do damage. And in this situation where you got a cap that's charging up and producing that impulse voltage, you just don't have it. No, if you go out and work at your lineman, you work on the grid, and you know the grid wires that come out, they're like on the order of 14,000, 15,000 volts, whatever it is. And yeah, I mean, you grab that and you grab a neutral, or you grab the metal tower that it's on with your other hand, you're going to get 15,000 volts worth of electrons pushed through your body, and it will continue to push through your body, and you'll be all burned up.
Okay. Makes sense.
Just to clarify, I'm assuming that's coming from the capacitor to generate that kind of voltage, correct?
It's the capacitor in combination with the coil.
Okay.
Hey, Scott, would you mind just showing? I'm just trying to understand the coil's what, charging up, and after it charges up, it goes
The
through
capacitor is charging up. The capacitor is charging up,
Okay.
supplying that charge to the coil. The coil stepping it up from whatever the input voltage is from the. Coil's basically.
Okay.
Rudy's asking, is the coil a transformer? Yes.
Okay.
Yep. So the capacitor, you can think of it like a battery, stores up charge for a bit and then can discharge that, and the coil steps it up, and that's how you get your super high voltage.
So it could only be for a very short amount of time, just for the fact that the capacitor is only discharge. It's good like once, and then it needs to go back and get more power. So that's why
Correct.
it's pulses.
Yep. That's what capacitors do. They charge and discharge, and they're used in all kinds of different applications. And it's they're not real big capacitors, so it can't sustain it. It's just once it discharges and it does it really fast, that's it. And then it's got to recharge, and it takes. Sam showed you that chart before. Like takes something less than a second for it to recharge.
Yep, like a quarter of a second.
Okay.
So yeah, and then just releases it all in one burst, which is perfect for generating spark, because all you need is a quick burst.
So again, the fix on this one was to replace the board. They didn't replace the sensor as well, correct? I mean, because
Nope. No, the temperature sensor was in spec, so there was no reason to replace it.
I guess I'm just trying to think that would be the only outside component that is making a decision to maybe stop the solenoid valve from, it's going to shut off because I'm sorry,
Yeah.
I'm talking.
No, you're right. I mean, you're seeing the entire schematic here. It's a pretty simple machine.
Okay.
Got
No,
a door
Tim,
switch here.
You're saying what
temp
I'm saying,
sensor.
Tim, that probably that the logic of the board that reads the temperature sensor was the faulty part on the board.
Okay.
Because
Okay.
that is the part that would tell
Right,
it to open up. And
That's
open up
the only
circuit.
external source that is giving it information.
Right, correct.
Okay.
Yeah, there's no other input to the board that could be lying to it, that could be telling it to not run
Got
the
Thank
burner.
you so much.
And since the temperature sensor is good, yeah, it has to mean the main board is misinterpreting
Right,
what the
so for
sensor is telling it.
temperature sensing, you've got the RTD, the temperature sensor, and then you've got a special circuitry not shown in the simplified schematic they give us that reads the RTD, and that circuitry is not uncommon for that circuitry to fail.
Gotcha. Okay.
And we deduce that because in test mode, the board actually work and all the components on the board, and it would keep the flame lit for an
Right.
indefinite period of time.
Yeah.
So what's the difference in there? And that would be the difference of the temperature sensing component of the board.
Right.
Right, so in
Yep.
test mode, apparently, the temperature sensing circuit on the board is disabled or not used, not read, not paid
Disregarded,
attention
yeah.
to, disregarded, that's it, yeah.
What is the Hall effect sensor doing on this? I usually think of them in washing machines.
Yeah,
Not
that
on
would
a
be
oven.
for the cooling fan here, because they want to make sure that that cooling fan is running properly. Otherwise, they'll overheat.
And this is a good question, Wally, too, because you'll see this on Bosch schematics as well. They show the cooling fan, and then a separate thing, they show the Hall sensor.
Yep.
Physically, these things are in the same place. The Hall sensor stuff is affixed right to the end of the cooling fan. So it's physical, and yet they're both changed at the same time. If there's a problem with the cooling fan or the Hall effect sensor, doesn't matter. You change the whole assembly, and you're getting a new cooling fan and Hall effect sensor because they're physically one component.
But electrically, they are completely discrete. They run on completely separate circuits. So it's one of those interesting, the difference between looking at a schematic and looking at the actual machine. The physical reality is different from the electrical reality.
Yeah, and the wiring diagram may show the wires all going to the same component, but the
Mhm.
schematic, because we're looking at circuits on schematic, shows them as separate.
Yep.
And Hall effect sensor, in this case for the cooling fan, is used by the board to monitor that rotation and to be able to throw an error if the cooling fan's not running or not running at rated speed.
Yep. Yeah, if the board wants to know if that cooling fan is running properly, because if it's not, then it has the potential to cook itself.
That's a good point. I was going to bring that up. I wonder if that was another potential problem. Is if that cooling fan's not running, is it shutting it down? But usually with the cooling fan, it would give an error code, or it wouldn't work in diagnostic mode.
Yeah.
It would also give an error code.
Yep.
Whirlpools and KitchenAid has been particularly bad about that cooling fan. The sensor on it, the speed sensor, is they're having connectivity issues to where when you order the new fan, it has a new harness attached to it, and it comes all as one with the cooling fan and the sensor on it as one. And they redesigned it with a different type of connector for the sensor.
Oh, so you have to splice in the Hall
No,
sensor?
it comes with it. It actually comes
Okay.
with it, and the new fan actually has that new harness on it.
Okay.
Yeah. A lot of times it will do a glucose buildup in the fan and it will not rotate in the proper speed. That's why the board throws error code. So it runs slower because of the glucose buildup.
Yeah,
That's
either
right.
of those. Yeah, both of those.
I just noticed something in the original topic here. Let me switch my share to the original topic. So here it is. He actually originally a while back, a number of years back, he went out on this, and it did have that fan too slow error. That's an interesting detail. Yeah, just what you were talking about, the fan throwing, or the board throwing an error for the fan running too
Yes.
slowly.
Yes.
Yeah, I love this call when the customer says, "Yeah, it's giving me a F8EO error." Cool, give me your model number, and you go out there with the fan.
Yeah.
Or
Yeah.
can the friction also build up over time, possibly mechanical friction, and it will run slower? Then the board knows that it's run slower because
Oh, sure.
it
Bearings,
it
bad
uses
bearings.
the bearings, yeah.
Grease and
All
Oh,
right.
interesting. Yeah. Actually, so he's saying here, okay, he's saying he replaced the fan back in 2017. Then he's saying he had to replace it again a few days before this job. So I wonder if the board failure was a follow-on from overheating.
Oh,
Hmm.
That's a reasonable thing
Very
to think.
reasonable.
If the fan was running too slow, then the board overheated a bit, cooked that heat sensing circuit. and that's how we got that. Because yeah, it was just a few days later.
Wow. Interesting.
Yeah, and then he never let it get too hot though, because he said set to 250. Fan came on before it reached temp, so it never got to 250. But presumably, we would have to say that it probably went longer than that 30 to 40 that 20 to 25 seconds that he writes in here as well. So
Yeah.
we kind of something changed between the set at 250 and fan came on before it reached temp, and now it's only turning on for 20 to 25 seconds.
Yep.
Yeah.
Interesting.